Hi, I would like to talk a little bit about measurements and what values um, can come out of measurements. We discussed before that in general, any wave function can be expressed as a sum of the modes of the Schrodinger's equation. In other words, as a sum of solutions to the time-independent Schrodinger's equation. Okay. So you solve your time-independent Schrodinger's equation, you obtain these modes, and then you can build any wave function in terms of the superposition of these modes. How to get these coefficients remains a question. In other words, you have to fine-tune and adjust these coefficients. It can be done. How to do this, we will not be discussing that. If you ever take a proper quantum course, you will learn. So for example, let's say the wave function, I'm not going to put the arguments. It's obvious that it's a function of space and time. Okay, it's obvious. So I don't always have to say it's a function of x and time, function of x and time, function of x and time. As you can see that it's a function of x and time. Okay, so for example, let's say it's C1 psi 1. It's a function of x. Fine, I'll remind you, but we really don't need to do that. E to the minus I E1 over h bar times time plus C2 psi 2 and x e to the minus I E2 over h bar plus say C7 psi 7 of x e to the minus I E7 over h bar times time. Okay. Now you measure energy. However that's done, that's a separate question. It's an interesting question. We won't discuss that either. Let's say you do perform an energy measurement. What are the values that your measurement can produce? It's an important question. After all, quantum mechanics is a theoretical machinery that is designed to predict what you measure in the lab. And so therefore, so far we've been talking about how to calculate wave functions in some very simple situations, how to calculate energies. We've been focusing a lot on the how to. Now we're stepping back and asking, well, let's say we do calculate the wave function. What does it predict as far as what we would actually measure in the lab? So for example, let's say you measure energy. You will get either E1 or E2 or E7 and nothing else. You will never get E8 because E8 is not represented in this particular sum, We also saw that the outcomes of measurements are random, but distributed according to some probability distribution. For example, we saw that with a double slit experiment. In the double slit experiment, we're not measuring energies. We're measuring positions. We could also use it to measure momenta, but right now, example is about energy. So you might get E1, or you might get E2, or you might get E7. You cannot predict before, whenever a particle is in this kind of quantum state, in this kind of wave function, you cannot be certain what value you're going to get. You can only predict probabilities. So the probability that you would get U1 is the square of the magnitude of coefficient C1. Remember, C's can be complex numbers. We can get E2 with what probability? With the square of the magnitude of C2. Or you could get E7 with what probability? With the square of the magnitude of C7. You're certain to get either C1 or C2 or C7. One of those three. Absolutely. Nothing else. But definitely one of those three. That means that, and you're certain to get a result. What that means is that the probability to get C1 plus the probability to get C2 plus the probability to get C7 must add up to 1. So therefore, okay? All right. So that's statement number 1. I hope you're seeing the pattern and realizing that this is not entirely new. You have already seen an example that's similar. We talked about superposition of the states of definite momentum. What is a state of definite momentum? What wave function corresponds to a definite momentum? Let's see, definite momentum means different wave number. Wave number, momentum, momentum, wave number. In quantum mechanics, measuring momentum means measuring wave number or wave number. So a state of different wave number is a plane wave, complex plane wave. And we've seen examples of a superposition of states of definite wave number. It's a different wave function. Okay, it's example 2. It's a different example, not this wave function, different wave function. Let's say we discussed that omegas and k's are related. How exactly they're related, that depends on a particular physical situation. In other words, on the particular potential energy that particle is subjected to. If it's a free particle, then we saw that omega is proportional to k squared. It's not a free particle. There's a different relationship. In all those cases, The relationship between omega and k is called dispersion relation. Okay, that's aside. Now coming back to this. So if I measure momentum, I could get either h bar k1 or h bar k2, respectively, with probability square of the magnitude A or square of the magnitude B. And I know that some students criticize me for making my H's and K's look similar. I get it. Okay. So now I hope you start to see a pattern. You can express, given a quantity, energy, momentum, angular momentum, whatnot. If you express a wave function as a superposition of states with that quantity well-defined, either as a superposition of states with well-defined energy, these modes of the Schrodinger's equation, or states of well-defined momentum, you can see what, when you express your wave function as a superposition of such states of a well-defined quantity, then you're going to get the measurement of that quantity will produce one of the values of that well-defined quantity that's represented in that superposition, in that mix. And the probability that you're going to get a particular value is given by the square of the magnitude of the coefficient. So if you express the wave function as a superposition of states of well-defined energy, such as in this example, you're going to get one energy or the other or the third. And you will only get the energies that are represented in that mix, in that superposition. And the probability to get a respective energy is given by the square of the magnitude of the coefficient that comes with that value of the energy. If you express the wave function as a superposition of states of well-defined momentum, then the momentum values that you could get out of the measurement are the momentum values that are represented in that mix. And the probability to get those momentum values are given by the square of the magnitude of the coefficient that comes along with that momentum value. Let's say I have something else, like angular momentum. We haven't talked about angular momentum, but angular momentum is something you could measure. And there exist wave functions that are well-defined angular momentum states. In other words, if a wave function is one of those wave functions that have a well-defined angular momentum, then you would always get one and the same value of angular momentum. If I represent a wave function as a superposition of those, let's say angular momentum value 1 and angular momentum value 2. Then when I do make the measurement of angular momentum, I'm only going to get angular momentum value 1 or angular momentum value 2. And the probability to get one or the other is given respectively by the square of the magnitude of the coefficient involved in that superposition. The square of the magnitude of the coefficient that comes along with the respective value of the angular momentum in that superposition. So this is an example. These are both examples of a discrete sum. We have state 1, state 2, state 3. But you can also have continuous sums. And we have seen examples of that. So this is a superposition of two harmonics, but you could also have a continuous superposition. Remember when we did Fourier transforms, we talked about discrete, and then you switched all the way, you switched that lever all the way to the left, and it became a continuous. So here's another example that builds on this momentum example with a continuous sum. So another example. I don't know why it's so thick. Continuous sum has a name. It's called an integral. Omega is a function of k. Omega is a function of k. It's not an independent thing. Okay. What is this thing called? That's just a Fourier transform. So I can get a whole band of results, a whole continuous band of results. In fact, I could get anything from minus infinity to infinity when I measure momentum, but the probability for that is set by the square of the magnitude of Fourier transform. That's really where that result comes from. Okay, so the probability density of momentum measurement outcome is the square of the magnitude of the Fourier transform. Why density? Why do I say probability density and not probability? So let's say it's some kind of a function like that. What that means is that the probability that a momentum value will lie in a bin of thickness dk, or that the wave number that you would get would lie in a bin of thickness dk around k, is given by this probability density times dk. Probability, now it's probability to get k, probability to get wave number between k and k plus dk. It's a k, not h bar, k is that's how you turn density into probability. That's how you turn probability density into probability. Mass density times a little bit of volume gives mass. Charge density times a little bit of volume gives charge in that volume. Mass density times a little bit of volume gives mass in that volume. Probability density times a little bit of amount of k space, k volume, k segment gives probability. Okay. So this is an introduction to this ideas of what you could get if you perform a measurement. There is another question one might ask. How does a measurement affect the wave function? We will not go there. Okay, when you take your proper quantum mechanics course, they probably will talk about the fact that a measurement drastically changes the wave function. It's a subtle discussion. It's subtle in part because one has to be clear, what exactly do we mean by a measurement? How is the measurement performed? So I decided not to teach that subject this quarter, in part because it's not discussed in your textbook. But let's summarize what I did say. Actually, I want to say one more thing. What about position measurement? Well, first of all, what is a wave function that corresponds to a state of definite position? It's basically a peak like this, infinitesimally thin with area 1 as a name. It's called Dirac delta function. So if the wave function looked like this, that means you would always get this position. Again, infinitesimally thin, then you would always get this position. And what if the wave function is something continuous like this? It's a different wave function. You can think of this as a wave function made up of a series of peaks, but these peaks are all represented with different amplitude. And the wave function is really the wave function at a particular x is just the amplitude with which that peak is represented. So therefore, this is the reason why probability to get a particular position is given by square of the magnitude times dx. And similarly here, you can think of the wave function as represented as a sum of little peaks like this, where each peak is a state of a definite momentum. And the probability and the amplitude with which each peak is represented is a of k. So the probability to get a particular value of the momentum is given by the square of magnitude of a of k times dk. You multiply by dk or dx because there's the probability densities. So you see, everything is now on equal footing. If you express your wave function as a superposition of states of definite position, then when you measure position, you would get a value, you could get a value x with a probability given basically by the square of the magnitude or the coefficient with which that position is represented. You multiply by dx because it's a probability density, it's a continuous distribution. You measure momentum, then you would get one of the values represented in the mix, in the superposition, with a coefficient that's given by the square of the magnitude, with a probability that's given by the square of the magnitude of the coefficient in front of the term with the respective value of the momentum. And if it's a continuous distribution, then you have to talk about probability densities, but it's still basically the square of the magnitude of the coefficient in front of each term. If your wave function is a superposition of states of different energy, then again, if you measure energy, then you would get one of the energies that are represented in the mix in the superposition with probability respectively given by the square, the magnitude of the coefficient that comes along with each particular energy. So you can see all these results are on the same footing. Now, what if you perform an ensemble of measurements? Say I have copies of the system, each prepared in an identical way, some kind of electron gun or something like that. And I measure a certain quantity, say energy. Measure in system 1, measure in system 2, measure in system 3. Well, in system 1, you might get C1, system 2 might get C2, system 3 might get C7, blah, blah, blah. You can talk about probabilities. You can also ask, what is the average value? What would be my average value? What would be the average measurement from an ensemble of this? What would be the average energy obtained from an ensemble of these measurements? What would be the spread, the standard deviation of my results? So you can ask statistical questions like that. The average value obtained from an ensemble of measurements, for some reason, has a fancy name. It's called expectation value. It's just a name. In the next lecture, we will talk about something called operators and how to use those operators to make a prediction of expectation values, average values. Okay? So this is part one. Now comes part two. Thanks.